Hello, students. I am Dr. Stuti Singh from ABES Engineering College and Applied Sciences and Humanities Department. So, in this lecture, we are going to talk about resolving power, Rayleigh criteria of resolution, resolving power of a grating. Okay, so we are continuing with the wave optics part 2, in which we have discussed about the diffraction phenomena, and now we are going to discuss about the resolving power. So why we are talking about resolving power? Because see, as already discussed in Enslet diffraction grating, that there is a formation of vibgyor. So if there is a formation of vibgyor and if we are able to see the all the vibgyor colors, violet, indigo to red separately, it means that the instrument is resolving that maxima very well. Okay, otherwise we would have just seen an illumination sort of. As our eye also resolve the images, na, two very close images separately. So it is said that eye is able to resolve. But now over here, we will be seeing that how the resolving power is working for grating theoretically. And with the help of telescope, we have already seen in the lab the resolving power of a grating as well as the instrument that was able to show you the vibgyor very in a very good manner. Okay, so what is the resolving power? Let us write down the capacity of an optical instrument to show two close objects separately is called resolution, and ability of an optical instrument to just resolve the images of two close points is called resolving power. So technically, that we were discussing, we can define the capacity of an optical instrument to show two close objects separately is called resolution, and ability of an optical instrument to just resolve is called resolving power. Okay, students. So now next we are going to discuss about Rayleigh criteria of resolution. According to Rayleigh, according to Rayleigh, as we are discussing Rayleigh criteria of resolution, so let us write down what Rayleigh talked about it. So see, according to Rayleigh, the 2 point sources or two equally intense spectral lines are just resolved by an optical instrument by an optical instrument when the central maxima of the diffraction pattern due to one source falls exactly on the first minima of diffraction pattern of the other and vice versa. Okay, so according to Rayleigh, the 2-point sources or two equally intense spectral lines are just resolved by an optical instrument when the central maximum due to one source falls exactly on the first minimum of the diffraction pattern of the other and vice versa. Now let us see what this, Rayleigh is trying to tell. So let us know this with the help of a diagram. With the help of diagram, we can make, suppose there are two, there are two lambdas. One is lambda and another is lambda plus d lambda. Okay. And this is at an angle theta. This is at an angle theta plus d theta. So the resultant intensity, if it is showing something like this, okay, this is the resultant intensity. So this resultant intensity is showing, it is showing what? This resultant intensity curve indicates no depend appears as if it is a diffraction pattern of only one spectral line. In this condition, the two spectral lines are not resolved. Okay, if we talk about violet or indigo, then these both are not separately visible as violet or indigo, or these both are not separately visible as first order Vibgyor and the second order Vibgyor. Let us draw another diagram. Now, when we draw another diagram, this is theta, and again theta plus d theta, or theta dash, we can say this is lambda and lambda plus d lambda. And if we are able to see, a slight dip between the two, okay, this is what? This is nothing but dip. If we are able to see this slight dip in the resultant intensity, then what is the condition? This is indicating that the condition are said to be just resolved. And what Rayleigh said the 2-point sources or the spectral lines will be just resolved when the central maxima of one coincides with the or falls exactly on the first minima of the other and similarly vice versa. So now this two spectral lines are just able to resolve. We can just find out that is not one spectral line like here, it is two spectral lines because it is showing a dip over here. This is the Rayleigh criteria of resolution, where the condition of dip is there, where the condition of just resolve is there. Okay, and when the instrument will be able to resolve the whole maxima separately, then they will be visible properly, or the spectral lines will be clearly resolved at theta or theta plus d theta. Then they will be able to resolve the spectral lines. Okay, so this will be the condition of the two. And this third diagram shows that they are totally resolved now. The condition of total resolution is showing over here. Okay, so this is the Rayleigh criteria of resolution. And this Rayleigh criteria of resolution also shows the intensity equation. The intensity equation of this is given by, see, what is it given by? So we can also, I can say that we can also define Rayleigh criteria in a different manner with the help of intensity. How we can define is, let us check. Okay, so according to Rayleigh, we can also write the intensity equation for the midpoint. What is that intensity equation? The distribution of intensity in a grating can be given by I is equals to I max. This is nothing but distribution of intensity in a grating. I is equals to I max. That is I max into sine square x upon x square. So for the first minimum, the value for first minimum, value of x is 5. And for the midpoint, for, we can say at the midpoint of two maxima, the intensity of the wavelength is obtained by substituting the value of x as 5/2. So for midpoint, x is 5/2. So when we calculate this, then I mid is equals to 2 times I max sine square 5/2 upon 5/2 cos square. That gives the value of 8 upon pi square into I max. So what we can write is that I mid upon I max is equals to 8 upon pi square. So the Rayleigh described the the Rayleigh described its criteria. It also stated that in a manner that it also stated that the two equally intense spectral lines are just resolved if intensity at the dip is 8 upon pi square times intensity intensity at either of the maxima. So this is also a manner of describing Rayleigh criteria of resolution, just resolved condition. Now, next, we are going to talk about resolving power of a grating or a diffraction grating. Let us talk about the resolving power of a diffraction grating. Because grating is also, when we are able to see the picture, it means the grating is also resolving that maxima very properly. So let us now check what is the resolving power of a grating. The resolving power of the grating, again, it is defined as its ability to show to show two spectral lines in a spectra separately. Separately. Okay. And no doubt this will be the definition that is defined as ability to show two spectral lines separately, as I discussed before also. The Vibgyor is formed, and if grating is making that Vibgyor or resolving the Vibgyor that Vibgyor colors violet, indigo to red separately, then it is having a good resolving power. It can also be defined it can also be defined as the ratio as the ratio ratio of the wavelength of any spectral line wavelength of any spectral line to the smallest wavelength difference to the smallest wavelength difference between neighboring lines between neighboring lines. Okay, let me write it here. Neighboring lines for which the spectral lines can just resolve at the wavelength lambda. Okay, so it can also be defined the resolving power as the ratio of the wavelength to the smallest wavelength difference. So in short, we know that mathematically how we are trying to show resolving power, that is lambda upon d lambda. So we are able to calculate lambda upon d lambda. Then easily we can calculate the resolving power of the grating, or we can check whether the two spectral lines are resolved or not. So resolving power is given by lambda upon d lambda. Okay, this is the resolving power of a grating. So to derive the expression for resolving power, let us draw a diagram. This is Enslet. Okay, this is suppose grating, and this is screen on which the two maximas M1 and M2 are forming at an angle theta and d theta. Fine. So with the help of these two, we are going to derive the expressions for lambda upon d lambda. So let nth principal maxima due to wavelength lambda be formed in the direction theta. As we can see here, lambda, okay, I'll mark, this is lambda and this is lambda plus d lambda. So lambda is at angle theta, and lambda plus d lambda is at angle theta plus d theta. So it is forming at angle theta. So what will be the equation then? The equation will be a plus b sine theta is equals to n lambda. Or if we multiply by capital N on both the side, then it will be a plus b sine theta is equals to n lambda, equation number 1, where n is the total number of lines on the grating, surface, and a plus b is the grating element. And this is also known as grating equation. This whole equation is grating equation. Now let us move further. What we are going to do is, now we have talked about the principal maxima that is forming at an angle theta. Now let us see how we proceed, because the direction of minima of this maxima is forming in the direction theta plus d theta. See, this is lambda, so this is maxima, and its minima is forming at which angle? Theta plus d theta. So now we are going to write the equation for the minima. So let the first minima, adjacent to nth order maxima be formed in the direction theta plus d theta. Okay, then from grating equation, what will be the direction of minima? The direction of minima is given by n a plus b sine. Now where minima is forming? At an angle theta plus d theta. That is equals to m lambda. And what will be the value of m in the direction of minima? The value of m will be n plus 1 lambda. Okay, so value of m is equals to n plus 1 because the minima is just forming by the side. Okay, at an angle theta plus d theta. Now, now according to Rayleigh, criteria, the spectral lines, the spectral lines lambda and d lambda will be just resolved when it will appear to be just resolved when nth maxima of the wavelength lambda plus d lambda falls on the first minima of the wavelength. And see in the diagram also we can see this, the minima of lambda plus d lambda is falling on the first maxima. So this is the condition of just resolve according to the Rayleigh criteria. Hence, what we can write is, hence, for nth maxima of wavelength lambda plus d lambda, we get, now this maxima is forming, if we write the grating equation, what will it be? Now this is forming at an angle, lambda plus d lambda is forming at an angle theta plus d theta. So what will be the grating equation? That will be, we will be writing a plus b sine theta plus d theta is equals to n. Now it is lambda plus d lambda. Okay, so this is equation number 2. This is equation number 3. And if now we again multiply with the help total number of lines in this, in a plus b sine theta plus d theta is equals to n lambda plus d lambda. This is equation number 4. So now we can see that this equation 4 and 2, we can equate these two equations, right? So let us equate these two equations. Equating 2 and 4. What we get? n plus 1 lambda is equals to n lambda plus d lambda. Lambda is equals to n d lambda. And what we were calculating? We were calculating lambda upon d lambda is equals to, then we were calculating the resolving power n. So from here, you can see this is nothing but the resolving power of a grating. And it is very clear from here that resolving power of a grating, it is depending on number of lines and the number of order. Okay, so we can also define resolving power as the resolving power from the equation number 5. What we can define is, we can define as resolving power of a grating is equal to the product of the order of the spectrum and the total number of lines ruled on the grating. Okay, so lambda upon d lambda is depending on n and n. So if n increases, then also the resolving power will increase. And if small n increases, then also the resolving power of a grating will increase. We can also write this equation as lambda upon d lambda is equals to n into a plus b sine theta upon lambda. As from grating equation, what is the value of n? N is equals to a plus b sine theta upon lambda. Okay. So this is another manner of writing resolving power of a grating. So now we are mathematically able to derive the expression for resolving power of a grating. That resolution you have seen in the lab, you have seen the pipcure. And if somebody, if somebody is asking you theoretical expression, then you can easily say, you can, solve that and tell that lambda upon d lambda is depending on number of lines and number of the order of the spectrum. Okay, students? Thank you, students.